Okay. So what we came up with was that, hey, well, the energy can change. We have three different variables, so either of those three variables can change, right? So we have can change the n, change the s, change the b, right? So the system can move in any of the ways as it pleases, depending on the constraints of the system. dn is not going to change in our box because atoms are not allowed to exchange. So this term is going to be 0 in our calculation. But you could theoretically think that maybe we could poke holes in the piston and allow atoms to exchange from one side to the other. And then dn may be changing, right? You may have some concentration gradient. And that concentration is going to move, and that's going to change the energy as well. So we have some components associated with this chaotic motion, the entropy, the disorder of the system, volume changes, some physical changes to the box, and of course the chemical changes to the box. And it's the sum of them. But as we noticed, or kind of asserted, was that you can't just write du is equal to dv plus ds plus dn. Internal energy is not just the sum of all the changes because they don't have the same units. Joules is, writing this would be joules is equal to meters cubed plus some unit which we haven't determined yet, plus n, which is moles, right? So they're all disagreed, right? So we have to multiply each of these changes by some conversion factor that converts the change in volume units, for instance, into change in energy units as a function of the volume. This is a slope in some sense of how the energy changes as volume changes. It allows us to interconvert between changes in one variable, changes in another variable, which is just a derivative, as we'll see. And so what we have now, again, are these differentials, these little changes in each of our variables, but they're multiplied by how the energy is sensitive to those variables. So if the energy changes a lot as you jiggle volume a little bit, then this is going to be a big contribution. But if the energy is invariant to the volume, it doesn't really care, then this value is going to go to 0. Or again, if the box is sealed and particles can't exchange across the piston, then this is naturally 0. Because nothing can move. Okay, so we have just a right. So here we can see that we're kind of doing very, very simple calculus here. We're thinking about derivatives in kind of an abstract way, but not in the way that we typically think of derivatives. This is more of thinking about how do we convert changes in input and understand how the output changes as we jiggle the input. Some things will be more sensitive to variables than the other, depending on the conditions. So we have to balance all three. What I want to do today is formalize this math a little bit so we can be on a more rigorous basis. And that requires just a little bit of calculus. And I wanted at the end of the class, is we needed to identify these sensitivities, these derivatives, changes in energy with respect to the variables. How does the energy vary? Variables, and we identify these three derivatives as experimental numbers or dependent parameters that we can measure in the lab. The change in energy as a function of volume is the inverse of the pressure, minus pressure. Okay, the minus sign is due to, we can talk about it later. It's just a notational issue. We just need it for the right sign. So the minus sign doesn't really have any physical meaning other than the energy goes in the opposite direction with volume as entropy does. So as volume increases, pressure, the value goes negative. And if you increase energy, the value goes positive. So they're just different by directions. That's all the negative sign means. So the sensitivity of the energy to the volume is just the pressure of the system. And we can kind of naturally think about that, right? If you have a constant gas, a number of small, imagine you have a balloon, right? That's filled with some amount of gas. And as you compress that balloon and squeeze it, right, you're increasing the pressure of the system, right? Because we're reducing the amount of volume. The energy is constant. We're reducing the amount of volume by squeezing it. We're assuming that the energy is not escaping, right? You're just compressing the gas inside the balloon. And so that means it raises the pressure, right? So the pressure is that response. An energetic response to changes in volume. Likewise, as we'll see, as you start to make your system more disordered, you start to give it more random motions and more ability to move around and do what it wants, then the temperature increases. And finally, as we'll learn later on, we'll come back to this, is that there's also a term that controls how atoms flow or particles flow from one component to another. Maybe there's a concentration gradient from, there's more concentration in box 1 versus box 2. The chemical potential is going to point the energy, saying that the energy is going to get better, or the entropy is going to increase in the system as particles move from box 1 to box 2. Right? Concentration gradients, and how strongly it wants to recover that concentration and re-equilibrate it depends on the value of the potential. When we talk about chemical equilibrium, when we talk about an equilibrium constant, meaning how a reaction is favored products versus reactants, that can be determined by evaluating the chemical potential. Chemical potential will tell us about chemical equilibrium. Right? So those are our big responses, right? These are the things that come out of the box reacting the changes in the input variables of the box in S and V. So let's
wait, sorry.
Yeah, go ahead.
Would you say that the chemical potential is like the strength of the concentration gradient?
Yes.
Okay.
Yes. In some sense, what it tells you is how much. Well, we haven't really talked about which way energy likes to go, because it could want to increase or decrease. We have to determine that. Well, let's say, for instance, that just like entropy, energy wants to be as high as possible, a maximal value. Right? So if we find that as moving particles from 1 to 2 is energetically favored, raises the energy, then the chemical potential will be positive. And the more positive it will be, the more the energy will rise per unit mole transfer. Okay, so a very aggressively product favored reaction is going to have a much larger chemical potential at the start of your reaction than one that is less aggressively product favored. And we'll look at those numbers in about half a semester. We'll come back. That one we're just going to ignore for a little bit. So again, what I want to do is I want to systematize this formula, this heuristic formula we came up with. I just want to make it a formula. And I want to make sure we have all of our ducks in a row and we understand each little component. And that requires just a little bit of calculus review. If you haven't taken Calc 3, there's actually some new topics in here, but I promise you they're not really any more complicated than Calc 1 derivatives. So I want to talk about this formula here. This du is equal to blah, blah, blah. We're going to talk today about the concept of partial differentiation. And what I want to think about is how the energy changes as I move one of the independent variables of my system. So imagine I have a box that only needs one variable. Okay, say maybe it's the number of particles or just something, right? There's no volume, no entropy, there's just one. So imagine a box, a constrained box. With constraints such that the total energy of the box, the internal energy U, is equal to a function U of one variable, which we'll call X, right? It's a one variable box. Maybe it's the size of the box or the number of particles or the density, who knows, anything. One variable that is independent. Okay. So now what I want to do is I want to think about how U changes as I move X. So I'm going to build a little, we're going to do it graphically. And let's plot X versus U of X. And let's think about how U changes as I move X a small amount. So let's say, for instance, I start at the point X naught, and the energy at X naught is right here. Okay, and then I'm going to move X a very, very small amount, dx, right? An infinitesimally small amount, with a little differential dx. So I can write another point on my x-axis called xo plus dx. Right? And then I can go evaluate my energy at that point, and maybe the energy drops like this. Okay. And of course, this is just a segment of a function that's defined for every point x. Well, maybe out here it goes up, and then maybe it's something like this, and it levels down like this. Something like that. And I want to think about du, right? I want to take dx to be very, very small. And I want to think about the infinitesimal change in u, right? I just want to calculate the derivative. Right, so the easiest approximation I can do, this is the classic calculus way to do it, is to say at point x naught, the change of u with respect to x is the slope of the line that's tangent to that point. Right, so I can draw a line that looks like this at x naught. Right? And the difference between the u at x naught and the u at x naught plus dx, this little gap right here, right, is du. Right, so this gap between the two green lines is dx, and this is the change du. Right, so we have a rise and a run, right? So we can write a slope for this line. Right, so rise over run is du over dx. Just a sec, sorry, lost my pen for just a second. Just got to recalibrate it 1 sec. Okay, there we go. Let me stop that. So du, here's freaking out. So du what is this line here? Well, du is going to be equal to, right? Well, think of that, it's equal to some function mx plus b, right? Think we're going to draw this line here that's tangent to the curve. And du is going to be some slope times the variable plus b. Well, let me write this as m. And so if we think about how x is changing, this means that du is some slope m times the small segment of the line along the x-axis, the difference between how much x is changing as we go from this point to this point along the line, which is just dx. So if we think of this as x equals 0, the next point of the line will be at dx relative. So we have some slope m times dx plus an intercept be? All right, so let's figure out what is the intercept of this line and the slope of this line. Well, we know what the slope is. By definition, from chemistry or from calculus, the slope is the derivative of the function at that point. So what we could write is that du is equal to du dx, which is the derivative of x with respect to u, evaluated at the point x naught. But when I write evaluated at a point, I'll write a long straight line, x equals x naught. This is just a number, and it's the slope of the tangent line at x naught, comma, u of x naught. Right? This little bar here means evaluated. Right? So it's just a number, so slope. So that's our slope. It's
So that
multiplied.
would be n.
Yes, that would be m times our little dx, our change in x. And what is b here? Well, b here is just the intercept of the line at x equals 0. Remember, what I've done is I've shifted everything. I've subtracted x naught from x. So this is 0, and this is dx. Oh. I've just shifted everything over a little bit. And so the intercept of this tangent line is just at u of x0, which is u of 0. Right? It's the y-intercept. So it's at u of 0, which is just u of x0. So whatever the point of the energy at that point, the starting point, that's our intercept. Okay, so here in one variable, we already see the structure of a change that we saw in that complicated formula of dn and ds and dv. We saw that the change in u is equal to the change in x times this sensitivity coefficient, this derivative that tells you how to convert between changes in x to changes in u, which is just the derivative of the function. Right, so this behavior right here is just exactly the same thing I wrote down for 3 variables, but here I just have it for 1. And here u of x naught, we have a problem. We don't know what that number might be. So we're going to have to figure out what this number is as well. Well, what we're going to find is that by referencing the energy of our system to a known standard, we can just set this to 0. We can set u of x naught to be anything we want because we're referencing it towards a standard energy reference. And so we can assume that the standard energy reference, say, is at energy 0, and we can just assume that this is also the case. So in general, we can always make this be 0 by referencing to a standard. We'll see that soon. So what we can say is that the change in a function, right? The change in a function is equal to the derivative of that function with respect to a variable times the change in the variable. That's 1/3 of that equation that we wrote down. So now the question is, how do we go from 1 variable to 3 variables, n, s, and b? How do we get that additional sum that we have? That's where we need to bring in what's called partial differentiation. So let's talk a little bit about partial derivatives, right? Again, don't lose this geometric idea about derivatives, that it's a slope of a line that sits tangent to that point. It tells you about how the function changes its value as you jiggle the input near that point. Well, that's not going to go away when we go to multiple variables. So let's imagine now just a quick, very simple example. that our energy now, just like before, is a function of our three variables, N, V, and S. All right, it's a three variable function. Now I can't plot this on a curve because I need 3 axes for inputs and a 4th for the output. So it's a 4-dimensional plot. So what I'm going to do is just pick 2 of them and plot the 3-dimensional cut. And then we can just imagine in our head by adding an additional dimension later on. We'll see that it's easy to do. So what I'm going to do is plot a 3-dimensional plot now. If you guys are not artists, you will be after this class. We'll draw a 3-dimensional plot now. And on the lower 2 axes, I'm going to plot 2 of the variables. We'll plot N and V. Right? So we're going to do this at constant entropy, as we say. Right? And then the z-axis, the one pointing up and down, is the output. Right? This is U. Okay. So let's imagine that we can, again, what we have here is not a curve like we had in the 1-dimensional, but we have a surface. Right? It's a 2-dimensional curve. The function of 2 dimensions. And so I'll just try to draw something. What's that? Yes, like a mountain. Exactly. Yeah, think like a mountain. So let me draw a very simple surface.
That's so simple.
Something like that. Okay, it's kind of like, it kind of looks like a really crappy water coming down and kind of bubbles down. Okay, it does. Right, so I can take any point on this surface, and I'll go ahead and kind of draw it in a bit more. You don't have to do this. I'm just trying to clean it up a bit. Who knows what it looks like? It just looks like some lumpy surface of values. And we can pick a value where our curve is. Right? And we can call this just like before. Let me make this a little longer. Right? This is going to be U of some N naught, some V naught, and our S value is fixed. So I'll just call it S naught. Right? So we have some energy at this condition, right? We've set our box to these 3 values, and this is our energy. Right? And imagine we can see this function, we can plot it. We can know how our energy changes as we move across the variables. So what I want to do is I want to think about how U changes as I go from this point to some other point, right? My final point. We're always, in this class, we're always going to be thinking about changes in things. Because once again, as we'll see, it's very hard to measure absolutes in thermodynamics. You have to have a reference for energy. We're always going to be thinking about changes. So we have some initial point, it doesn't matter. We have some final point. Go ahead and put a final point there. Let's say it's right here. I'll do a different color. Yeah. And this is going to be U of N naught plus dN. V naught plus dV, and entropy is constant in this system because we're not plotting it, so it's S. Okay, and I want to think about the total change in U as I move all my variables, my 2 variables, right? I want to think about how is U changing as a function of dN and dV. Well, I can certainly draw a straight line from 2 points that's tangent to that point. Right? Imagine I have a curve that looks like this, just like before, that's tangent to that point. Right? I could certainly calculate the slope of it. And it's going to be a complicated combination of changes in N and changes of V. But I can decompose point motion from here to here in a slightly different way. Instead, sorry, go ahead.
So you're not talking about the tangent on the plane, you're talking about a line that connects through both values of u.
Well, okay,
Both
so
dots.
it's D is small enough. D has to, the definition of a derivative is that D is small enough that the tangent line connects both points.
Okay,
All right, so just, I'm exaggerating the distance.
okay, I see it.
Okay, so. Right, because Angie's exactly correct, right? The function could oscillate wildly between these 2 points, but the assumption we make in calculus is that the difference between this point and this point in terms of variables is infinitesimally small. We're just jiggling a tiny amount. And so you can always assume that it's going to be linear in that regime. If it's a differentiable function. The function has a derivative that exists, and it says that as d gets smaller, you can draw a line between those 2 points of tangent. That's what a derivative is. So I can figure out algebraically what the slope of this is, and that's great. But I can make it simpler. Instead of going the bird's eye direction from one point to another, I can do a different analysis or breakdown of how energy is changing. What I can first do is just change n first. Right? I could go to this point here, which is where n is changing, right? So this point would be u of n naught plus dn, but v and s have not changed. Right? And then what I can do is I can walk down the volume direction to finish the trajectory. So I do it in 2 steps. And so this little purple change, I know it's getting a little small here. This little purple change is dn, and this green change here is dv. So instead of changing n and v together to get to the final point, I can move one stop and then move the other. Right? Just run along the length of the triangle instead of the hypotenuse. Right? The total change in u is the same between both ways. I haven't done anything different. I've considered how n changes or how the energy changes as I change one variable than the other, and I end up at the same point as if I just crossed as a bird did from point A to point B. Right? It doesn't change the energy at all. Now I'm doing more work. You imagine I'm a hiker. It's going to take me more work to go from here to here than it is to just go straight across or as a bird, right? That's not what I'm asking. What I'm asking is how much does the elevation of this mountain? Sorry, that's probably my wife. She knows I teach. Yes, it is her. Right. Sorry. Right. So even though the hiker has to travel more this way, the total change in the energy is still the same regardless, because I go from this point to this point, and I'm only changing the output. So du changes the same amount from this point to this point, regardless if I take the scenic route or I take the direct route. Right? So I get the same result. Right? I just break it into 2 chunks instead. Right? Well, that's really, really nice because we just derived how to think about how a function changes with one step. Right? We know how du changes as one variable moves. So we can calculate that. And then we go for the next one and just add them together. Right? So what we could say is that du then is going to be the change along n and plus the change along v. So that's going to be du dn times n, or sorry, times dn. And then we walk down the volume, and du changes by du dv, dv. Okay. So we just come back to that equation, right? And then if I add the next one, entropy, we get that equation back that I had before from last class. Right? So a change in the derivative, the total change of a function can be represented as just the sum of the changes of each of the individual variables. Summed together. These are what are called partial derivatives. They're called partial because they express only a part of the total change of the output with respect to the input. So I need to clean up our notation a little bit. So we just need to do a little notation. So we're all consistent. Nothing's changed about our discussion here. But I just want to notate my partial derivatives because I use this notation a lot. So what we call, there's two different types of derivatives. There's a standard derivative or a total derivative. That we typically write, let me write, so like for instance, for an example, if U, the energy is just a function of X, then du is equal to the derivative, the total derivative of U with respect to X times dx. And this is just a regular old derivative. All right, what you learn in Calc 1, right? And anytime you say remember dy dx, that's the same thing. If you can calculate the derivative of the function with respect to x, and we just plug it in. Right? A partial derivative is like a total derivative, but it's the change in the function along one variable holding all the other variables constant. So a partial derivative is just a derivative, but done only along one trajectory, one direction, one variable. And we have a slightly different notation for it. So a partial derivative is the rate of change, or the slope, however you want to think about it, of a function as you vary a single variable holding all others constant. All right, so let's do an example. Just notationally. Remember, we defined the derivative of energy with respect to entropy as the temperature. Okay, we need to clean up this notation a little bit. What does it mean for this to be a partial derivative? When I write a partial derivative, I will use these little squiggly little d's. All right, let's compare the d's a little bit. So a total derivative, I'll just kind of put it in a box here. We write as, say, du with a normal English d, lowercase d, and a partial derivative, we use a squiggly one or a curvy one.
It's not a sigma, is it?
No. It's an italicized d. Okay, so anytime you see that, you think partial derivative. Okay, I will sometimes be lazy and interchange them because they're very similar to each other. There's one more thing we need to add. Okay, remember the key point about partial derivative is that we're looking at the rate of change of a function along one direction, but all the other ones are held constant. So I will always write the variables that are being held constant, and I write them in the subscript of the derivative. And so what I would write here is n and v, and this is saying that temperature is the derivative of u with respect to WRT with respect to S holding n and v constant. Okay, and I'll give you these a little more distinct squiggles. Okay, so that's just a little notation. So squiggles, I have this down here, some things that are being held constant, I have the Wiggles thing partial derivatives. It means that the upstairs function is a function of multiple variables, and we're thinking about the change along just one of them. So that's really, really convenient for us, is that the total change in a function is just the sum of the individual changes of each of its variables. It couldn't get any easier. So let's just do a quick math example. All right, let's just do a partial derivative just so we're all on the same page, right? There aren't any special rules about partial. There's a few, but they're not important. But all the rules of regular differentiation, regular derivatives apply to partials. There are a few exceptions. There are actually partial derivatives have some simplifications that we don't have to worry about right now. But let's just do an example, right? So let's just say, for instance, we have a function of f of xy, which is x squared y plus sine of x log of y. All right, crazy function. Absolutely absurd function, but really easy to calculate the derivatives of it. Let me show you how. So again, this is a function of two variables, so we have two derivatives. We have one along x and one along y. So first we'll calculate the derivative of f with respect to x, holding y constant. Right? And so what we do is when we go into our function, we're going to treat x as our variable that we're differentiating, and all the y's you can just think of numbers as numbers. They're fixed. They're just numbers. So this is just a coefficient on the outside of x squared, and this log of y is just a number. Just a number. So this is just a function of something that looks like y times some functions of x. We know how to do these derivatives. So we need to take the derivative of x squared. What's the derivative of x squared, everybody? 2x, thank you. So this is going to be 2xy. And what's the derivative of sine of x? Speak up. Cosine, thank you. Oh, there it is. That's it. Right? We hold those other variables constant, and then you just treat them like numbers, like coefficients on a variable, algebraic variable. Easy as that. And let's go ahead and calculate the other one. All right, so now we're differentiating with respect to y. Our x's are numbers. So this is just a y function. What's the function? What's the derivative of y? Yeah. 1. So this is x squared. And what's the derivative of log of y? There you go. Sine of x over y. Right? And so I could write the total derivative of the function called df. Let's sum these up. Right? And remember, df is the partial derivative of f with respect to x, holding y constant times dx, plus the derivative of f with respect to y, holding x constant times dy. All I have to do is plug and chug, right? The total change in f is going to be 2xy plus cosine x ln y dx plus x squared plus, sine x over y dy. Okay, I'd say the math's not too complicated. You know, if you're comfortable with regular derivatives, partial derivatives are just an extra step. I'm going to give you there's an interesting property about second partial derivatives, taking a derivative of a partial derivative that I will have you explore on the homework. There's a simplification you can make with second derivatives. And second derivatives, as we'll see, are very useful. Thinking about curvature, how functions approach a minimum or a maximum quite a bit. Very important in science. Right? And the second derivative is just in some sense as important as the first derivative. We'll look at that on the homework. Let me stop for a second. Any questions so far? Yes, ma'am.
Are we able to like partial derivatives like f of x or f of y, like f sub x?
Oh, that's fine too. I can read that. Yes. Yes. If you're comfortable with that notation, that's okay with me. That's a very engineering or in physics oriented notation. But that's totally okay with.
That's how they teach in calculus.
Is it? Oh, okay. Yeah, so this would be f sub x, and this is f sub y. Okay, all right, so let's continue on. So now that we understand a little bit about partial derivatives, let's go back to our thermodynamic equation of U, V, and V and S and just kind of put everything together. Okay, so now what we can say finally is that du is du dn, or sorry, du dv, right? It's going to be a constant number and entropy times dv.
That's a total DU, right? Like that's.
Yes, this is the total change in u. Yes, big du. Try to make it as straight as possible when I write that. And here, I'll give these a little squiggly. Like that. And these are partials. Du ds holding v and n constant times ds plus du dn holding v and s constant times dn. All right, so that's, yes, go ahead. I'm sorry. Yes.
So you said that earlier, or in yesterday's lecture, you said that we could, depending on the situation, you could replace S with T.
Yes, we'll do that.
All of
yeah.
this would be the same.
Yes,
Okay.
absolutely. Yes, in fact, what you would get then, if you replace S with T, you would get du dt times dt. And du dt, as we'll see, is the entropy.
Yes.
Okay, so they're interconverted between the two. Actually, I think it's minus entropy. There's a minus sign. But you can kind of see this, that what we're going to see is that entropy and temperature in some sense are what we call conjugate variables. They're circular references to each other, and depending on your constraints, you can either define S independently, like we are right now, or you can define T independently, and S is a dependent variable. We can interchange. And in fact, we can do that for any sets of variables that are conjugate. We will be able to, for instance, I'll write it in a second and we can talk about it. We'll come back to it. So just to put our things down, let me just simplify this with some notation. Instead of writing these partial derivatives all the time, let's just write it down the way that it looks prettiest, which is that du is equal to TdS minus PDV plus mu dN. Right? All of it together so that the total energy of our box changes with these proportionality constants as we vary the three parameters. This is what's called the fundamental equation. Let me write this in better text. The fundamental equation of thermodynamics. It is our Newton's law. This is not, and hopefully we'll have some time on Tuesday to give you a little context. We definitely will. This is not the original way that thermodynamics was derived. We'll talk a little bit about it on Tuesday. We'll talk about how a man named Henry Joule, the namesake of the unit of energy, discovered that energy in his mind can be partitioned between two different things, which are called work and heat, which you guys have a very intuitive understanding of. It's a very intuitive way to think about energy. Work is energy being used for something orderly, like pushing or pulling, moving a piston, something that causes the gas to do something constructive. And then heat is all the other stuff, right? And what we've done, instead of thinking about work and heat, we're going to find that using work and heat leads to a problem with the math. Right? And the reason why this equation was developed after the fact was that those problems with this idea of working heat are disappear. And that this is an exact equation that you can integrate and you can do all the calculus and the algebra that you would ever want to, and it's consistent. And so this is a reformulation of the original thermodynamics from the 1800s and late 1700s. Done by someone very, very near and dear, maybe not to this school, but to this city. This was developed by a man in the late 1800s named Josiah Gibbs. You guys remember Gibbs free energy? This is the namesake of Gibbs free energy. We'll talk about Gibbs free energy in this class quite a bit. But
I'm
Gibbs,
guessing he went to Yale.
no, did he go to Yale? So it's complicated. He lived here his entire life. I think he went to Yale. He taught at Yale. His son taught it, and his children went to Hotchkiss School. And he lived and died in Yale. And for a long time, he was the one of two chemists at Yale. He wasn't the first chemist that Yale hired, but he was like the second or the third. And he spent his entire life here in New Haven. In fact, it doesn't exist anymore, but the old chemistry building at Yale was called Gibbs Hall, and it was on Gibbs Hill, Gibbs Science Hill, and that's where his old office was, and that's the origin of Yale chemistry is Josiah Gibbs. Gibbs made the Yale chemistry department truly world class in the late 1800s. And so all of modern thermodynamics sourced here in New Haven. Funny enough, Josiah Gibbs was a revolutionary. He came up with this. He was, in some sense, 20 to 25 years ahead of everybody else in Europe at the time. He never published in any European journals. He only published in regional New England journals. He was a local guy. And so he published this reformulation of Joule's thermodynamics that changed everything. I mean, this is what we still use to this day. The most modern theory of thermal. Well, it's not the most modern theory of thermal. There's a more modern one, but don't worry about that. We'll talk about that later. There's another way to think about this, but it certainly in terms of kind of like engineering and thermal physics and thermodynamics, just kind of traditional engines and things like that. This is what drove the Industrial Revolution's equation. But the Europeans had no idea about it. The Europeans had no idea. It wasn't until Gibbs died that papers started to get sent over. They were getting discovered, get sent over to Europe, and people were realizing that Gibbs had figured these things out 20 years before they did. So this is truly local science. Truly local science. Okay, so let's use this equation now to solve our piston problem. We have now tools to solve our piston problem. Okay, I just wanted to make sure I have my notes so I don't screw up the math here. Let me just put this in a box. We will return to this equation many times throughout the class. It will be as I said, it's like our Newton's equations. It looks complicated, but what we're going to do is we'll make simplifications to it. That'll be our first goal, is to make it simpler. So don't freak out. So let's go ahead and let me just rebuild my piston just so I have it. I've got this piston in the middle. And I have I'm just going to write it in terms of the energy, the moles, and the volume. Remember that we can interchange between U and S freely. They're invertible functions, so we can represent it either way.
T.
So we have a function. So let me answer that. So effectively we have four numbers floating around for this box. We have the internal energy U, We have N, we have V, and we have S. Okay. Remember that one of the properties of S, the entropy, is that it's a singular invertible function. Every value of U, N, and V corresponds to a unique version of S. So
Oh,
there's
right.
right. So we can interchange between U and S freely if we want. So we can write S, we can write this as instead of measuring U, we can measure S. We have a apparatus that measures the entropy. That's a function of U, N, and V. Or we can construct a box that measures the internal energy U, which is a function of N, V, and S. Okay. And I'll interchange freely between them, whatever seems to be convenient. But they're freely convertible. So the most important thing that we should note here is that the energy is conserved in the box. The box is closed. There's no energy leaving or going. So that what that means is that U1 plus U2 is constant, right? We wrote that down last class. And this means that the change in the total energy, or the change in U1 plus U2, right? The total change of the energy is 0. Right, which immediately tells us that d u1 is equal to minus d u2. Again, very trivial, right? If we lose energy in one side, it has to go to the other. That's all this is. Okay, what else do we know about this box? Remember, we're trying to calculate the position or the condition where the box, where the piston stops. Right? So this piston's going to move around freely, and eventually it's going to find a position it likes and it doesn't move anymore. And there's a condition that it has to satisfy. Remember that the condition at equilibrium, our equilibrium condition, oh, that's a B, not an E. Is that the point, the entropy, the change in the entropy at the final point is 0, and that the second derivative of entropy is less than 0. So it's a maximum. Okay, so we know that wherever the piston stops, ds is 0. Right? Because we're on a stationary point in the entropy. So what that means is, what we can say then, is that the change in the entropy of the first box, the first compartment, plus the change in the entropy in the second compartment is also 0. Right? If one's 0, the other one has to be 0, because the whole entropy is 0. And we can also write that the total entropy, right? Remember, it's just a linear function, so we can just write it as S1 plus S2. Right? And that is a function S, which is a function of variables N, V, and U. Okay, so again, I'm just writing a lot of things, but just asserting that what I can do, instead of writing a function U, I can write a function of S, which is also a function which takes U in. Right, so I'm just interconverting my two variables here, and I want to do that because I know that the condition where I end is where the function, entropy function, is flat, right? ds is 0. So I'm on a maximum. So I'm going to think about the energy or the system as a function, or as entropy instead, right? Entropy as the dependent variable, because I know that it flattens out at equilibrium. So what can I do with this information? Well, what I can do is calculate the total derivative of S with respect to N, V, and U. But that's really, really easy to do because the change with respect to N is 0. The change in the total volume is 0. And the change in the total number of particles is 0 as well. Right? Because the volume is conserved and the particle number is conserved. So all I have to do is say,
0 plus 0.
well, hold on a second. Hold on a second. That's not necessarily, the total thing is 0, But what I can do is think about how S varies as the energy moves from one box to another. U can change, the energy can exchange. The particles in the volume cannot. Right? So what I can write is that the total change in entropy is equal to the change in the entropy of the first box with respect to its energy times the change in its energy. I'm just calculating partial derivatives at constant V and N, plus the change in the energy in 2 with respect to the change in energy in 2 times the change in the energy of 2. Now, the important thing is I'm kind of casually moving between total and compartmentalized energies, right? I've gone from total energy to sums of smaller parts of energy. Well, the total energy doesn't change, but that doesn't mean that each part doesn't change. The parts can fluctuate, but we know that the fluctuations are anti-correlated to each other. If one goes up, the other one must go down because the sum is conserved, but the individual values are not. The sum is conserved. So one can move up, one can move down. Right? And depending on where the piston is, we'll change the signs. If the piston wants to move towards box 1, one of these partial derivatives is going to be positive, and the other one's going to be negative. And because of the conservation, remember that if U1 goes up, U2 must go down. So DU2 is just equal to minus DU1. Right? I can just change my variables. I'm just doing a little bit of algebra here. So here's my first term. And now what I can do is substitute DU2 with respect to DU1. This term right here is equal to minus DU1. Right? If energy U2 goes up, energy in 1 goes down. So I'm given now that you get a negative sign. But the U changes to 1. So now what I have is that the total change in entropy of my box, which I know eventually goes to 0, is just a function of the change in energy. I can just track one box. If I know the energy, how the energy changes in one side of the box, I know how it changes in the other. So I lose a variable. I have one. So now what I have, all I have left now are 3 terms here. I have this change in U in the first box, and then I have these 2 partial derivatives, ds du. Now let's go back to our definition of the Gibbs energy, or the Gibbs equation. What is du ds? At constant volume and number.
It's T, yeah.
Right, so what's ds du?
ds du up 1 over T.
1 over T. So these are inverse temperatures. Remember, this whole thing has to be equal to 0. All right. So this is equal to 1 over the temperature of the first box times its change in energy minus 1 over the temperature of the second box times the change in energy. And that's equal to 0. Okay, so wherever the piston stops, this equation, du 1 over T1 minus blah, 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 1 over T2 is equal to 0. Where is this true? What condition has to be satisfied algebraically for this to go to 0?
T1 equals T2.
Exactly. The only place where this goes is when the temperatures are the same.
So the piston will always move until
Until the temperatures equilibrate. So the pistons stop. I'm running out of space here, but I'll just write it at the top, or I'll just write it here in the corner. Piston stops when the temperature is the same in both. Temperature has appeared. Where has temperature appeared? Temperature, in some sense, we haven't been able to measure temperature at all. We've said that, hey, if I can measure the energy and the entropy and I can figure out the slope, I can determine the temperature. But again, the only thing that we can do is think about change. We have to have a reference to describe absolute energy. You have to have a standard. But what we've done now is we've had two boxes that can exchange energy with each other. And so now, in some sense, they reference each other, right? One soaks up the other's entropy and vice versa. So we have two boxes that may be at two different positions in space, in the sense they have different energies, different numbers, so on and so forth. But we know that we're guaranteed that the system is going to equilibrate and reach a stable place for all time when the piston stops. And where does the piston stop? Where the temperatures are equal to each other. So this gives us a way to define temperature. Do I have time? I do. This allows us now to create a temperature reference. Because now imagine box 1 is an unknown gas of unknown energy and temperature. And box 2 is a gas of known energy and known temperature. You can figure out what the temperature of gas 1 is by watching the piston move until they equilibrate. You know one box already, so you can reference the other box to it. Temperature arises from a comparison of two different things approaching equilibrium. So what is our standard definition of temperature? I want to be very precise about this. So let me just pull up all the notes I have for this. I don't want to make this wrong. Okay. So there are different temperature definitions in science, right? I'm going to choose one today that we'll typically use in this class, that is chemical. It's a chemical temperature one. We'll call this the chemical temperature scale. Temperature scale. There are different ways to calibrate temperature, but this is the way that the chemists do it. All right. So a standard box of energy. We can create a standard box of energy by creating a box and placing inside of it water. Water gas, water vapor, right? So we have a box of water. And I'm going to define the conditions of this box slightly differently than we have before, but they should all make sense to you, right? Nothing crazy. We're going to define the temperature of this box to be 273.16 Kelvin. And the pressure of this box, we haven't really talked about pressure yet, but we will, is defined to be a very specific number. I'm going to give it to you in a couple different units. 0.00604 atmospheres. So just a reminder, if you don't know what an atmosphere is, it's atmospheric pressure. 1 atmosphere is right now, a fraction of an atmosphere. Another unit that we sometimes use is the SI unit for pressure. And I'll go through these a little next week. We'll see them more often. 611.657 pascals. This is the SI unit of pressure. So this is, as we'll see later in the class next week, this unit is newtons per square meter. Right? It's a force applied on a surface. It's a force over area, surface area, so as a pascal. So that's our SI unit. Right? And this is what's called the triple point of water. Right? It's a specific point where this is literally what 273.15 is defined as the specific physical point in water's phase diagram called the triple point. And at this point, liquid water, gaseous water, and crystalline ice water are all at equilibrium. Right? The idea is if I change the temperature or the pressure, I can end by a small amount. I can end up in any three of the phases. Okay. Maybe you've never heard of the triple point, and that's okay. We'll do phase diagrams and you'll learn about it. Every pure material has a triple point. Well, I can prove that to you. Every material has a triple point, and we use water's triple point as our definition for temperature and in some sense pressure. Okay, so this is our chemical temperatures. Right, so how do I use this? Well, I fill my right side of my box with my triple pointed water. Put my left box, my unknown molecule or my unknown material at some energy and some number, and I watch the piston move. If the piston compresses the water, that means that the temperature of the gas, sample gas, is higher than the water. If the water compresses or has more energy, if the water compresses the sample, we know then that the water is hotter. Okay? So if we can understand how the energy changes, or say how the volume changes as the temperature differential is, I can measure the temperature difference. I can measure how the volume moves. Can I calibrate that to a temperature difference? And the answer is yes. If the piston moves just an inch, I know that the temperature is different by some amount. If it moves a foot, then I know the temperature is much greater by some amount. So I can calibrate that curve. I can calibrate distance of the piston to the temperature of the unknown gas relative to this box. Does that make sense to everybody? This gives us an absolute scale. In some sense, I can't tell you how much energy this box has. But we can calculate. That's not the important thing. What's important is how does the sample we're concerned about, how does its energy content compared to an equivalent box of water at its triple? Is it more energetic or less energetic? And all that means is the temperature higher than 273 at this pressure or lower than 273 at this pressure? That's all it means. Okay, so temperature, what temperature is, what we're going to see is that temperature is a measurement of entropy change in a system. That's one definition of it. We're also going to find in the next week or so that it's a measurement of the average energy of a sample relative to our water reference. We'll be able to correlate total energy of the box with the temperature as defined compared to our box of water. And most importantly, perhaps, is that temperature is what do I want to say? A condition or consequence of what we call thermal equilibrium, right? This is that concept of the piston stopping when it reaches an equilibrium. What is the definition of a thermal equilibrium between the piston and the two boxes where the temperatures are equivalent? The temperature just measures, in some sense, the average energy of a material but it's also a way for us to track how energy is flowing from one system to another and when it's gonna stop. So that's where we are with temperature. What we're gonna start with next class is to use temperature to our advantage. What we're going to do is put our box in a system that is at constant temperature. So it always has a reservoir of energy to pull from or to dispose of. Right? Well, think about systems that are at constant temperature and how they work. That'll be very, very useful for chemistry because guess what we do in chemistry a lot of? Things that don't change in temperature. We set the temperature of a reaction to 25°C and we keep it there. So we'll start to think about what we call isothermal conditions where the temperature is not changing, and then we'll think about the other ones as well. Keeping entropy constant, keeping numbers constant, keeping pressure constant, keeping volume constant. We'll start to constrain the systems, but what we're going to find is we're going to start to find out all of these little features of reactions and enthalpy and Gibbs free energy and all of these terms you took in Gen Chem, they all fall out of this math. Okay. All right. You guys have a nice weekend. Thank you. You don't have to clap for me. Jesus Christ almighty. Jeez Louise. If you're really that appreciative, please send an email to the provost or the president telling them that I'm the best teacher you've ever had and that I should get a paper.
Yeah. We also never did this survey thing. We still gotta.
Yes, that Tuesday.
Oh, I thought you, okay.
It's Tuesday. Yeah, I didn't have time to finish the presentation, so it'll be Tuesday. Yes.
See you on Tuesday.
See you then.